All right, good morning, chemists. We'll get started here. The snow didn't stop us in this 8 a.m., but I didn't see a lick of salt on the road, so I'm worried about my commute home. So we'll see about that, but we'll still learn chemistry today. All right, so on Tuesday, we left off talking about activation energy and how it relates to this new equation, the Arrhenius equation. So I mentioned we will never actually calculate K using the Arrhenius equation, this form of the Arrhenius equation. We can get it experimentally using the integrated Arrhenius equation, but this equation tells us the trends of how rate constant, small k here, changes with different factors. So we see that K obviously increases if A increases. That A term is the frequency factor. Essentially, it takes into account orientations and how our collisions occur. And so if we have really efficient collisions that lead to chemical reactions, A will be a large term. So that's specific to what kind of reaction and what kind of conditions you have. But more importantly here, what we can grab from graphs and things that we can measure, we see that K increases when temperature increases due to the nature of this math, that it's e to the exponent negative EA over temperature. R is a constant. It's our 8.314 joules per mole Kelvin. R, not our gas, well, it's still the gas constant. R, but it's just a different unit. So as T increases, all right, T increases, K will always increase. But more subtlety here is that we have another term, activation energy, and what we see here as well as activation decreases for a specific reaction, we also see K increase, and that's just with the mathematics behind an exponential here that has a negative exponent. And so, we compared these two different reactions, exo and endothermic reactions. We see that if these are to scale, this reaction, this endothermic reaction, has a larger activation energy. You've got to get up a bigger hill. And so just from this picture, we see that this reaction, the endothermic one, will be slower overall because it has a bigger hill to get over. All right, so that just goes along with the trends that that I just overviewed here. But more important subtlety is, okay, well, what if we take these reactions and change the temperature? Like I said, as temperature increases, K will always increase. But the difference is here is these two reactions will respond differently. And when we look at this example with using the integrated Arrhenius equation, we see that both reactions, if we heat them up, will increase their rate constants. They'll get faster. But the one with the larger hill will get faster, I guess, more, all right? That it'll change, that rate constant will change more because its activation energy is larger. And so that's why the answer here is C. Both will increase their overall rates and specifically their rate constants, but this endothermic reaction, C to D, will increase more. This will be an important point when we get to chapter 15. All right, so keep that in your back pocket for chapter 15. All right, okay, how K is related to activation energy and temperature there. All right, so let's do the mathematics here, and I'll show you the tricks for solving questions like this. All right, so we have a single reaction that we're studying under two different conditions, two different temperatures here, and we're studying the rate constant. I tell you that the rate doubles when the temperature is increased from 20 degrees to 60 degrees. So you might think, oh, the temperature's tripling, but it's not necessarily, because this is the Celsius scale. So just like with gases, we want to make sure our temperature is in Kelvin when doing these calculations. So T1, just quickly convert that to Kelvin here. Oh, I don't like that. Can I do this one? Yeah, okay, there we go. T1, add 273, so this is 293 Kelvin, and 60 degrees Celsius is 333 Kelvin. All right, so we have two different temperatures, a reaction at two different temperatures. So I'm just going to define 20 degrees as T1 and I'm going to define the higher temperature as T2. Because I didn't give you rate constant, like an actual number, but that's okay, because I'm telling you that the rate doubles. So let's just say this. Let's just say the rate constant for the first temperature is 1. Let's just say that. What is the rate constant for reaction 2, the higher temperature one? 2, yeah, because I told you that the rate constant doubles, all right? So we got to start somewhere, all right? And so associating the correct rate constant with the temperature is important here. That at T1, at 20 degrees, the reaction's slower. At 60 degrees, it's going to be faster. So I'm just going to assign K1 as 1, K2 as 2. And so I have here a bunch of reactions, or sorry, a bunch of equations that relate to the things we've been talking about. So the things to note here, we have 2 different temperatures. We want to calculate activation energy. What equation do we use? The first, second, third, or fourth one? The third one, yes. So let's talk about that a little bit. I already had it circled, so whatever. But the idea here is, okay, this equation has 2 different temperatures. All right, it has 2 different rate constants, and we see that when we plot this linearly, I showed an example where we had 4 experiments, but we can do this with just 2 experiments as well, because 2 experiments always make a straight line. The slope of that line gives us activation energy with a factor of R in there as well. So this is the equation we want to use. At first glance, you might want to use this equation, but what's the problem here with the Arrhenius equation? There's no T1, T2. There's a temperature, yeah, but there's not 2 different temperatures. I integrated it for you, so use the integrated Arrhenius equation. Oh, what about this one? This one has stuff too. But again, there's no T1, temperature 1 and 2, so we can't really use this equation. If we had a bunch of data, and we plotted it, then we could use this equation. If we actually got a line of best fit from a graph, we would use this equation to inspect it. Okay, so now at this point it is plug and chug. You just want to make sure everything's in the right unit, everything in its right place. Because if we look closely at this equation, note that it's natural log of K1 over 2. Then we have our activation energy, and in parentheses, it's inverse T2 minus inverse T1. So you just have to be a little bit cognizant of that. I'll mention sometimes this equation is represented this way, where it's negative EA over R, and what we have on the other side, and it's still 1 over T2 minus 1 over T1, but then this is ln K2 over K1. Sometimes it's represented this way, but again, if you know anything about natural logs, if you flip the number inside, you get this negative sign that comes out, right? Ask your math teacher how that works, but these 2 equations are in fact the same. They're the same equation, it's just we flipped this on the inside. So you will be given the one I circled. The one I circled is the one that you'll get on the exam. Okay, all right, great. So let's plug everything in. Okay, so natural log of K1 over 2. So we want to put 1 over 2, right? I think you might want to put ln of 2 because the question says the rate doubles, but we want to again be cognizant of it's K1 to K2 doubles, but what we put inside the natural log is 1 over 2, not 2 over 1. Okay. All right, equals activation energy. That is what we're solving for. R, which I'll just put in that number right now. Okay, so we're solving for activation energy. R is 8.314 joule mole Kelvin. 1 over T2, so we already took inventory of our variables here. So the 333 number goes first, 293 Kelvin. And again, this equation won't work if you leave everything in Celsius. So it needs to be in Kelvin. All right, and then we just solve for it. Do I have that work? All right, so if you do this side of the equation, you get negative 0.6931 equals, and I'm just going to do all this math here, including that 8.314 in the denominator. So EA times negative 66 point, oh no, never mind. I'll just leave that R there. EA over 8.314. So in the parentheses, that number is negative 6.6 times 10 to the negative 4. All right, so move everything around and we get that activation energy is equal to activation energy over R. That value is 1,150. All right, and so multiplying both sides by R, we get a value of 8,731. So the small detail here is what is the activation energy unit? I ask you to give me the activation energy in the units kilojoule per mole. Is this value that we just plugged and chugged into our calculator, is that in the unit of kilojoules per mole? What is its unit? It's joules per mole. How did we get that? Is that something you just have to memorize? No, so the detail here is that R, it's going to match the unit of R. R is in the unit of joules per mole Kelvin. We got rid of the Kelvin because we got some, temperature stuff there. So the unit of activation energy is kind of embedded within our R unit. It's in joules per mole. All right, so that means that this reaction, its activation energy is about 9,000 joules per mole, but we want to, typically we talk about activation energies in terms of kilojoules per mole, so it's 8.7, how many sig, 2 sig fig, 3 sig figs, times 10, 8.73 kilojoules per mole. There we go. So that's a small detail that activation energy is typically given in kilojoules per mole, like if you look up at a table, you'll see it in kilojoules per mole, but when you use activation energy in this integrated, the 2-point Arrhenius equation, you want to make sure that it's in joules per mole so it cancels with that unit of R, 8.314 joules per mole Kelvin. All right, good. Okay, so in this example, we calculated activation energy. Did other people get the same number? Did you all get the same? No, you did not get the same? Yes, half? Okay, okay, my work might be a little bit off, so let's do this. Okay, 333 inverse minus 293 inverse divided by 8.314 natural log of 0.5 divided by that number. What? Yeah, I'm wrong. Wait, hold on. Okay, natural log of 0.5 divided by negative 4.0. Oh, this number is wrong. What the heck? This number is wrong. I'm sorry about that, guys. Okay, so within the parentheses here, it is negative 4.099 times 10 to the negative 4. Does that look better? Does that? Yes, okay, all right. All right, so we're off by a little bit. So 0.6931 divided by 4.099 e negative 4. Okay. Okay, we're off by a little bit. So 6, 9, that looks better? Yeah, all right. Great. Times R. There we go. Okay. I can make mistakes. 14.058. There we go. 14.1 kilojoules per mole. Yay. All right. So sorry about that. Yes, do check your math. Do check your math. All right. Other questions here? Questions. Okay, so in this example, we calculated activation energy because we were given 2 experiments, all right? The rate constant and the temperature for 2 experiments, although we had to kind of like imply what the rate constants were here because we weren't actually given a number, but we said that it doubled. Another way we could ask questions like this is I could give you a rate constant and temperature for one reaction. I could give you the activation energy, and I can ask you to predict the rate constant at another temperature. all right? And so in that case, we would know one of the Ks, we would know activation energy, and we would know both of those Ts. Again, just make sure you associate the correct temperature with the correct reaction, and then we would solve for the missing K. So that's the other way we can do it. All right, so that's activation energy and temperature. So there's the overview of that. We looked at a bunch of different equations derived from the Arrhenius equation. We get our trends from the Arrhenius equation. K will always increase when temperature increases or when activation energy for a reaction lowers. We can calculate activation energy graphically by looking at the same reaction conducted at different temperatures. If we figure out what K is at a bunch of different temperatures, we can plot it and basically look at the slope within there to figure out what activation energy is. All right, it will be EA over R because that's the slope within there. Or if you don't want to do it graphically, right, you don't want to do like 3 or 4 experiments, we can just look at 2 experiments. And so really these 2 equations are basically the same. It's just we've kind of simplified it to just look at 2 different experiments at 2 different temperatures. Or sorry, it's the same experiment at 2 different temperatures. You just have different Ks, rate constants there. All right, so that is the Arrhenius equation. So I think we can put our calculators away for a little bit, all right, because we're going to do the last part of this chapter, which is another way to determine the rate law. All right, we've been talking about the rate law a lot within this chapter. We've already looked at 2 different ways to determine the rate law for a chemical reaction, the different ways that we can figure out a rate law for a chemical reaction. The first way we did it was the method of initial rates. All right, initial rates where we, did the same reaction a bunch of times where we just change the concentration of the reactants, and we see, okay, if we double the concentration of reactant A and the rate doubles, then what is the order for reactant A? 1, right? Or if we see, we double reactant B and we see a ×4 of the initial rate, that's an order of 2, right? So that's the first way that we can figure out the rate law for a chemical reaction using initial rates. I like that one. It's like, okay, this doubles, that doubles, it's 1. If and things like that. The second way we did it, and folks don't like this method, is the graphical method. All right, graphical method, where we actually have to determine what the change in concentration of reactants, how it changes with time. That's not time, that's temperature, with time. All right, so if we actually track a single reaction with time and we graph those concentration changes with time, we're looking for a linear line, right? And so when the graph fits a linear line, depending on if you graph it 0th order, 1st order, or 2nd order, when you find the right graph that makes it linear, that is the order for that reactant. So that's the second way. So that means for the second method, you actually have to pull out Excel in order to do, you could do it on your calculator, but graphing it via Excel is the easier method. There to see, okay, you can easily, change your columns and graph it to see which one gives you the most linear line. And so this last method, reaction mechanisms, is the last way to figure out what the rate law is. So this is the third method. All right. And so with reaction mechanisms, we're basically trying to predict how are the reactants actually interacting with one another, so bringing back collision theory. So we're going to be looking at simple reactions, what we call elementary reactions, to inspect how those chemical reactions occur and then how we can get a reaction mechanism. All right, so in 1210 we talked about chemical reactions, and we calculated their enthalpies, their reaction enthalpies. We broke all the reactants and formed all the products and calculated delta H of reaction, where we broke all the bonds, and formed all the products. But the thing is reactions don't happen that way. We don't break all the Lego pieces and put them back together to make products. It's much more subtle and specific to certain reactions. So when we look at a balanced chemical reaction, we're basically just looking at what reactants we start with and what products we form. That balanced chemical reaction doesn't tell us how reactants actually interact with one another to form these the products on the other side. If we look at this chemical reaction and kind of think, okay, how is this reaction occurring? You might think, okay, this NO2 is losing an oxygen, and that oxygen's going to CO. Do you see how that kind of looks like that? But in the background, what's actually happening on a molecular level, that might not be happening. It might be a little bit more complex than that. It's not just this NO2 giving up an oxygen, giving it to CO. That might not be how it is. So this is where we use reaction mechanisms. Reactions might actually happen in more than just one step. Something breaks, something forms. There might be steps there, and that's what we're going to be looking at. So these mechanisms, these are basically we're trying to explain how bonds are breaking and formed in each step. All right, so with mechanisms, what we want to inspect are what we call elementary reactions that produce the multi-step mechanism that results in our overall equation. All right, and so the important thing when determining a mechanism is that one, it needs to be consistent with the balanced equation. When we add up all of our steps to our mechanism, it has to produce the balanced chemical equation. It's like Hess's law, right, where you just add up all the reactants, add up all the products, cancel out things that are on the same side. It's the same thing there. So we need to make sure our steps add up to our overall reaction. The second thing is we need to make sure that each elementary step, it is consistent with the overall rate law that we usually determine experimentally. All right, so let's do an example. No, not yet. Okay, so what is an elementary reaction? Basically, it's the simplest interaction between molecules within a mechanism. So remember how I told you when we did rate laws and stuff? All right, and determining order for our rate law, that you cannot just use the coefficients in the balanced equation to be order. You can't do that, right? You got to do it experimentally. So in elementary reactions, you can do that. In elementary reactions, these simple one-step interactions between molecules, the stoichiometry of the reactants does become the reaction order. All right, so these are basically our simplest chemical reactions overall. So there's different types of elementary reactions, and it depends on how many molecules are involved in the interaction. So for example, a unimolecular reaction only involves a change in one molecule. So this second picture right here, this would be an example of a unimolecular elementary reaction where we have one reactant, right, and it's just breaking apart. That's a unimolecular elementary reaction. So what is the reaction order for this? For that reactant? Just one, because in this example, elementary reactions, the stoichiometry is the reaction order. So this unimolecular reaction has a reaction order of 1. Okay, the next one is a bimolecular elementary reaction. It involves a collision between two molecules. So if you look closely, look at the reactants. So this first picture is a bimolecular elementary reaction. We have two molecules interacting with one another. It looks like it's changing bonds here, and you produce products. So in this example, what is the order of this reaction? It would be 2, yes. The concentration of this red molecule, the order would be 2. And then, so finally, a termolecular elementary reaction is when 3 molecules interact to form products. The thing is that this is not very common. Statistically, it's very unlikely that 3 molecules will collide all at the same time in space with one another, so it's not super likely. But following the trend here, if we did have a termolecular elementary reaction, what would the order be? 3, yes, it would be. But again, it's not super likely. Third order elementary reaction is not super common. All right. Oh, so what about this picture? What about this picture? What's the order for this? This would be, yeah, second order, depending on the concentrations of both of those. All right. So this is a bimolecular interaction here. Okay. Because we have 2 different particles interacting. All right. So those are elementary reactions. So I mentioned that when we build a mechanism, we need to make sure that our elementary steps add up to our overall reaction. So we can relate this to our energy diagram and the idea of activated complexes. So looking at this energy diagram, just looking at it, okay? Okay, if you're over here, and you want to get to products, how many steps do you have to get through to get there? 2. Yeah, you have 2 hills to get over, right? You have 1 activation energy there, okay? And then another one right there. So this is step 1, and this is step 2. So step 1 is 1 elementary reaction. Step 2 is another elementary reaction, all right? For fun, which step is slower? The first one or the second one? The first one. Why? The activation energy is higher. Yeah, the hill is higher. So that first step is going to be the slow step here. Okay. So if we look at, so here I have at the bottom here the actual elementary steps for this specific example. So let's say A plus B have to interact with one another to get over that first hill. So that is our first step. Our second step is, okay, so the product we make from step 1, A, B, come together, it makes this new compound, AB. The second step may be, okay, you take that AB substance and it reacts with another B atom that's floating around, and that's how you get your product. So the idea here is, again, elementary steps add up to the overall chemical reaction. So when you add these 2 things up, you see, okay, the product of step 1 is the reactant in step 2, so it cancels out. So do you see how those 2 elementary steps add up to the overall reaction? So you see A plus 2 B atoms give us our product, A, B2, or whatever. All right, so the kind of subtlety here is the compound AB that we formed in step 1. Does that show up in the overall reaction? No, it doesn't, but we formed it. So AB is an example of an intermediate. Okay, so AB is an example of an intermediate right there, all right? That you need to form AB first because it is the product for reaction or step 1. So AB lives right here in this little crest. So remember what I said about, the difference activated complexes. Now we're talking about intermediates. Can we isolate an activated complex? Can we actually get it? Like if we did a reaction, could we put it in a jar and store it for later? No, we can't. We cannot isolate an activated complex. It's at the top of this hill. If you put a ball at the top of this hill, it's not going to stay there. It's going to roll to either direction. But can you isolate an intermediate? Yes, you can, because it's in this energy well. So again, if you put a ball there, it's going to stay there, all right, in that intermediate state until you give it more energy to go in either direction. Okay, so let's answer these questions. Can you isolate an intermediate? Yeah. Can you isolate an activated complex? No. And so the important thing here, don't just memorize that idea, the difference between intermediate and activated complex. Look at it, think about where those substances exist on our energy diagram. Okay, so great. Oh, and then what's this last question? Which step is predicted to be the slowest step? 1 or 2? 1. 1 is the slowest step, and therefore it's going to have the smallest rate constant. And we'll come back to this idea in a little bit. Okay, so moral of the story, a sequence of elementary steps results in our overall reaction. This is a multi-step mechanism. Okay, great. All right, so I mentioned how rate laws relate to our elementary steps is that the molecularity, okay, whether it's uni, bi, or termolecular, determines the order for that specific reactant. So I told you you were not allowed to do that. Just relate coefficients with orders back at the beginning of this chapter, but in terms of mechanisms and specifically elementary steps, you are allowed to do that. So here you see, okay, for this unimolecular reaction, if there's only one reactant present involved, the rate law for that step is just A to the order of 1. If it's bimolecular, then it's A squared in that case. Okay, these two reactants are the same, so it's two A's interacting, but we can also have a bimolecular reaction where it's A and B coming together. So the rate law is, for that elementary step, is the rate is, K, the rate constant, times the concentration of A and B. So when you look at the overall order of this rate law for this third line here, what's the overall order? 2, because 1 plus 1 is 2. All right, so see how that's all coming together. I told you weren't allowed to use coefficients as orders, but you are allowed to in elementary steps. Okay, and I told you termolecular reactions aren't very common, but let's get the rate laws for these last 3. So what would the rate law for this one be? It would be A to the 3. Yeah, because there's 3 A reactants. Do products matter here? Did the products matter? No, they never did. Products never mattered for rate laws. It's always concentration of the reactants, the things that are combining, that determine the overall rate of a reaction. All right, the next one. What would the rate law be? A to the 2 and B to the 1. So you see that the overall rate order for that, the second to last example is 3, because 2 plus 1 is 3. All right, and the last one here is K times concentration of A, concentration of B, concentration of C, with an overall order of 3 for this termolecular reaction. Okay, good. So those are our elementary steps. Okay, so, all right, so how do we actually get a rate law from these elementary steps? So we'll work on that next, but let's do an example here where we actually get the overall reaction. So I'm giving you a mechanism. I'm telling you these are the steps, step 1 and step 2. These are elementary steps. When I say the word step, it usually means elementary reaction. All right, so keep that in mind. So we have 2 different steps here. So let's think about what is the overall reaction. So to get that, we just add those 2 steps up to see, what cancels. So let's see, what is the overall reaction? So I like to see if anything cancels. Does anything cancel when we add up these 2 steps? HI, yeah, so HI cancels. Does anything else cancel? No. So basically we have these 3 substances are our reactants. So H2 plus 2 ICLs gives us, remember that HI cancels, looks like we have I2 and 2 HCLs. So that is our overall reaction. Overall, okay. Let's determine what is the molecularity of each step. So step 1, what do we think it is? So uni, bi, ter, whatever. What is it? Bi, yes. And the second one? Also bi, yeah, because there's 2 things interacting. Great. So let's determine the rate law for each step. So step 1, the overall rate of that specific step is equal to K, so some K. I'm going to call it K sub 1 because it's the rate constant for step 1, times the concentration of H2 times the concentration of HCl. That's it. All right. And then the second one is going to have a different rate, so I'm going to give a rate constant. I'm going to call it K2 because it's a different rate constant, is equal to the concentration of HI times the concentration of ICL. So that's it. You just take, so yes, finally we are allowed to just take coefficients, turn them into exponents here. All right. Next here, any intermediates? What are our intermediates? HI, yeah, because that's the one that canceled. Anything that cancels on either side would be an intermediate here. Okay, great. All right, so what's my next slide? Okay, so what does this reaction actually look like, and how can we get the rate law? Because right now, we have the rate law for each step, but we don't have the rate law for the overall reaction. That's what we care about. We care about the overall reaction as chemists, not necessarily the actual, single steps here. We want the rate law for this. So how do we turn the rate laws for the steps into the overall rate law? So let's think about this. So let's pretend, that this is the reaction that's happening, right? From this diagram, this reaction happens in how many steps? 2, yeah. So we start here. We got to get over one hill, and we take a long dive there, and then we end up here. All right, this is where once we're kind of in that little crest, this is where our intermediate lives. What was our intermediate? I think it was HI was our intermediate. But then we interact with our intermediate, go over the next step. So this is a two-step mechanism. All right, and then we get our products here, where we consume our intermediate in this middle step. And so remember, whenever I give a reaction coordinate or whatever, I usually typically ask you which step is slower, right? It's usually the one with the higher activation energy. So that's how we're going to be able to get our rate law. This diagram, it's not super obvious which step is the slow one. So we'll move on to another example where it's much more obvious, hopefully. Okay, so for determining the rate law for an overall reaction, it's always the slow step that determines the rate law for the overall reaction. The slow step always determines the rate law for the overall reaction. Go to bed tonight and say that 10 times. The slow step always determines the rate law for the overall reaction. And so this is what I'm talking about. If I have 80 steps in a mechanism, the slowest step always determines the overall rate law for that chemical reaction. And so the analogy we use to talk about this is, if you think about there's basically 2 scenarios that we will study in this class, but the analogy is like, okay, you have a highway, you have cars driving along the highway, and you have toll booths, okay? And we want to think about, okay, what is the rate of cars exiting the freeway? So if the first toll booth is the slow toll booth, let's say there's only one worker there, all right, and all the cars pile up at that first toll booth, that is the slow step. That's the rate determining step. Because once a car is past that toll booth, it'll just, fly through the next toll booth. And so that second step's not affecting the overall rate because it's fast. Versus, all right, so that's basically example 1. That's scenario 1, where the first step is the slow step. The second scenario is, well, what if the slow step is the second step? All right, and these ones are harder to calculate. Where, okay, the cars fly through the first toll booth, but then they start piling up at toll booth B, the second toll booth. And so the overall rate in which cars get through this highway is determined by that second step. So these are the 2 different scenarios that we will study. We approach them differently, all right? So the first one. Okay, actually, no, not yet. All right. So in this class, okay, we talk about mechanisms, we talk about steps. You will never be asked to propose a mechanism. Yes, I know, right? Right, yeah, no, that's outside the scope of this class. Instead, we typically ask you, is a proposed mechanism consistent with the rate law? All right, so you need to be able to, if I give you a mechanism, you should be able to get the rate law. That is the learning objective here. We give you the mechanism, you determine the rate law. And we'll ask questions and ask, like, is this consistent with experimental data? That's how we typically ask questions like this. Because the detail here is that a mechanism actually can't be proven correct. I can give you a mechanism, but it's just proposed. The reason we can't prove that it's right is because we can't see atoms. We can't see atoms. I can't put my binoculars on and see, okay, A is colliding with B. I don't actually know that. All I can see as a mere mortal is, experimental data. If I change concentrations of stuff, rates change, that's all I can see. I can't actually see atoms. So mechanisms cannot be proven right. But can a mechanism be proven wrong? Yes, it can. If we propose a mechanism and it's not consistent with the rate law, then that mechanism is not right. So we can prove mechanisms wrong. We can't actually prove them right. So instead, how we ask questions is we ask, is the mechanism consistent with the rate law? All right, so yeah. Okay, great. Or is it consistent with experimental data? So that means from the experimental data, you need to figure out the rate law and then compare that to the rate law of the mechanism and see if they match. So there's two types of mechanisms we're going to look at in this class, and it's the two car examples. The first one where the first step is slow, right? That's the easy one. And the second one's the harder one, is if we have a slow second step. So those are the two we're going to look at. And again, I want you to go to bed tonight and say this over and over and over, is that the slow step is the rate determining step that determines the rate law. Good, okay, so let's do it. So the first one. Okay, so I'm giving you the overall reaction, and I'm giving you the proposed mechanism. I told you, you will never propose a mechanism. Okay, let's just make sure, do these two steps, do they add up to the overall reaction? So if we look here, we're combining two NO2s, we get NO3 and NO. It looks like NO3 is being consumed again. So NO3 is what kind of substance? It's an intermediate, yes. It's getting consumed, it's reacting with a CO, and it's making products. So if you cancel those two intermediates out, you do get the overall reaction, where we have NO2. Okay, NO2, do we? Yeah, NO2. It looks like there's actually two NO2s and a CO. So I'm just adding them up. Gives us a NO2, an NO, and a CO2. So you might be thinking, well, there's two NO2s here, but there's only one in the reaction. What's a small detail here too? Is that we're actually producing an NO2 as a product, so one of the NO2s actually cancels out. And then we do get the overall reaction, all right? So basically, these two cancel out, and those cancel out, and so we do get the overall reaction. Okay, so based upon this mechanism, I'm just gonna delete all that so we can see it. What step is the rate determining step? The first one, yes. Okay, so this is the rate determining step. Okay, so remember, it's the rate determining step determines the overall rate law for the reaction. So let's write the rate law for that slow step, just like before. So the rate equals K, some type of K, I'll just call it K1, times the concentration of NO2 squared. All right. So if that's the rate law for the slow step, the rate determining step, what is the rate law for the entire reaction? The same thing, yes. So again, the slow step always determines the rate law for the entire reaction. So in this example, the rate for this reaction is just K1, so the rate constant for that first reaction, that first step, NO2 squared. So what is the order of this reaction? 2. So if I changed, if you were given experimental data and you changed the concentration of CO, would it change the rate of the overall reaction? No, it wouldn't. But if I doubled the concentration of NO2 in this as the reactants, how would the initial rate of that reaction change? Times 4. Yes. So that's how we would relate it back to previous data. All right, so this rate law, if this mechanism is correct, where that first step is the slow step, it needs to be consistent with everything else, all the experimental data we talked about previously. Oh, cool. So according to the rate law, how would changing concentration of CO? No change. Cool. But if we changed NO2, we would see a change. Okay, so that's it. So let's do another one. Was that okay? Yeah, that's the easy one. All right, let's do this one. Decomposition of hydrogen peroxide is that. What's the overall chemical equation? Okay, so let's do this. So it looks like these IO minuses cancel. What else cancels? What else cancels? I minus, yes, I minus cancels right there. So if we rewrite this, it's H2O2. It looks like there's two of them. Arrow, oh, someone needs to wake up. 2 waters are produced and an oxygen. Yes, there we go. So that's the overall reaction. So what's an intermediate in this reaction? Yeah. So yes, we canceled out 2 different things, but they're a little bit different. Think about what an intermediate is. You gotta produce it, then consume it. So now that I said that, an intermediate, you produce it, then consume it. Which one is the intermediate? IO minus, yes, that is the intermediate. So then what the heck is I minus? What is I minus? I minus in this case, because it's a reactant, it's kind of acting as a reactant, but then it's being produced again at the end. I minus is actually a catalyst. It's a catalyst in this reaction because we add it, but it's regenerated at the end. So then it can be consumed again, all right? And so catalysts, that's how they work. It's like a reactant that's never ending, essentially. All right, so I minus is actually a catalyst, and we'll talk about it later. Okay, all right. So what is the rate law for this process? A, B, C, or D? What do we think? Do we know? How do we get the rate law for the overall reaction? It is always the slow step. So what is the rate law for the slow step? It would be A. Yes, A. Where we just take the concentration of the reactants for the first step. That's it. Cool. All right, so that question's a little bit too easy. All right, so instead we'll ask questions like this last one. Which energy profile is consistent with this proposed mechanism? The first, second, or third one? Okay, well, so what's wrong with the first one? There's only one step. Yeah, it's only one step. So it can't be that first one. Okay. All right, so what's the difference between the second one and the third one? Yeah, so in the second one, the slow step is the first step. Okay, this is the slow step, because once you get that intermediate, then it's just a small little hill that you get over. But in the second picture, it looks like, okay, the activation energy for the second step is a little bit larger. So in that third picture, the second step is the slow step. So I think, yeah, that second one is the correct energy profile diagram for this picture. Okay, great, great. All right. Okay, let's do another one. Okay, where on this reaction coordinate diagram would the concentration of IO minus be the largest? A, B, C, D, or E? What do we think? So remember, we already said it. What is IO minus? It is an intermediate. Where do intermediates live? In this, yeah, so it's C, because we produce the intermediate, all right, so we have to get over that first step. Look, IO minus is a product of the first step. So you think, okay, going from A, going over this hill, that's how we get the products of our first step. Then the products of the first step are involved in the second step. So IO minus is, the concentration is largest in C. Great. All right. All right, what's next? Okay, one more. All right, so this is another way we can ask the question. So here's a reaction. That's the rate law. What mechanism is consistent with this rate law? What do we think? So I think what's easiest here is just figure out what the rate law is for both of the mechanisms and see what matches. So what is the rate law for the first reaction, this first one? It's B, oh sorry, no it's not. This one, it's again, the slow step determines the rate law, so it is concentration of A, concentration of B. So does that mechanism fit our experimental data here? No, it does not. So it can't be that first one. And for fun, let's just check that adding up these two steps results in the overall chemical reaction. So in this case, M is our intermediate. So we get 2A plus B gives us CD. Is that our overall reaction? Yes, it is. Let's check the second one too. Oh, this is 3 steps. Oh my goodness. So, but still, we add them up. M is again an intermediate. Is there another intermediate being produced? Yes, N is also an intermediate. And so hopefully you can see that when you add these 3 reactions up, you still get 2A plus B gives us CD. All right, it's just different mechanisms. Okay. So what is the rate law for this the second mechanism? Just B. All right, it's just K times B. So which mechanism is consistent with this rate law? The second one, so it's this one. Okay, good. So that is, yes, that's the easy one, where the first step is the slow step determines the rate law of the overall reaction. So let's do the harder one, where the slow step is actually the second step. And typically with these types of reactions, there's a small assumption. It's the second step that's the slow step, but the first step is a fast reversible reaction. And that's the big idea here. The first step is fast and reversible. The second step is the slow step. So let's just go through the process. So let me propose you a mechanism. There's some mechanism, all right? The overall reaction, what would it be? It would be 2A plus B gives CD. That's the overall reaction. That's the overall rate law we want to determine. Okay. So tell me, what is the, so again, for all reaction mechanisms, it's the slow step is what determines the overall rate of the reaction. So what is the rate law for the slow step? It is K2, because in this case it's the second step, it's K2 times the concentration of B times the concentration of M. K, great. So are we done? No, because what's the problem here? M, is that in the overall reaction? No, so do you add M to the reaction to make this reaction go? No, M is not in the overall reaction, so it cannot be in the rate law. So we need to get rid of M. And so here's the trick of getting rid of M, which is an intermediate. So with all of these slow second step things, we need to, there's always going to be an intermediate that we need to get rid of, right? So yeah, M can't be in the rate law because it's an intermediate. Great, so we can't have that. So maybe you think, oh, let's just get rid of it. Let's just delete it, cancel it. No, we can't do that. So this is how we approach it. We're actually going to use the first step to help us. So the trick to get rid of M is to use the rate law for the first step. So because the first step, so I just copied it down here, because it's fast and reversible, it means that the forward rate and the reverse rate are equal to one another. Okay, following me? So if I'm telling you the forward rate and the backwards rate, they're equal to one another. If we go forward in this reaction, what kind of molecularity is it? Is it uni, bi, blah? Bi, yeah, in the forward direction, 2 A's are coming together, it's bimolecular. But what about the reverse reaction? Is it also bimolecular? No, it's unimolecular, all right? So we just need to write the rate law for the forward reaction, write the rate law for the backwards reaction, and set them equal to one another. So this is how we do it. So the forward rate is equal to what? K1 times what? A squared equals the reverse rate. Is it K1 again? No, it's K negative 1 now, because it might have a different K rate constant for the reverse reaction, times the concentration of M, because in the reverse reaction, the product is now the reactant. Okay, do you see where we're going? Yes, so now we have this equation that has the M term. So what I'm gonna do, solve for M. Okay, solve for M and take those variables and shove it into the original slow step. That's it. So, so if we solve for M, M is equal to, come on, M is equal to K1 over K negative 1, A squared. All right, and so this is the term that we're going to plug in to our original one that had that M term we weren't allowed to have. All right, and so that's it. So the new rate law for the entire reaction is equal to K1, K2 over K negative 1 times A squared times B. That is the rate law. Okay, is that one harder? Yes, this kind is harder, where the slow step is the second step. Okay, and so the idea here is still that idea of the slow step determines the overall reaction rate. We can't have an intermediate, so we use the fast reversible step from step 1 that's typically given. We set the rates of the forward and backwards equal to one another so we can solve for that intermediate concentration and plug it back into the original. All right, so that's the harder one. But those are the only two kinds that we'll give you. Those are the only two kinds. All right, so how do we feel about that? Okay, let's just do more practice. Okay, all right, so let's determine the overall rate law for all of these reactions. I'll just straight up tell you. So it says, what's the balanced reaction? They're all the same. They're all 2A plus B gives us CD. They're all the same. They're all the same overall reaction, just different proposed mechanisms. So let's get the rate law. I think we already did these two. What's the rate law for this first one? It's just A times B, all right, because the slow step is the first step. All right, okay, so what about this second one in this corner? The overall rate is K times just the concentration of B, because again, it's the slow step determines the overall reaction rate. But then the other two are different, right? The slow step isn't the first one, so we gotta do a little manipulation. So here is my strategy. Again, the slow step always determines the rate. So in this example, the rate is equal to K, I'm gonna call this K2, times the concentration of B, times the concentration of M, but we're not allowed to have M. Oh, this is the same example as before, but it's okay, we can just do it again. All right, are we allowed to have M in the rate law? No, we can't. So I'm going to take the fast step, set the forward and reverse equal to one another. So I'm gonna say K1 in the forward direction is equal to A concentration squared, because it's bimolecular, equals K reverse, the rate constant for the reverse reaction, times the concentration of M, because that's the reactant of the first reaction. And so you move those things around to isolate M. You get M equals K1 over K2 A squared, and so then you plug that in, and you get that the rate for the overall reaction is K1, K2, K negative 1, B, A squared. So a small thing to note is, yes, I have different little k's all within the front here, so like K1, K2 over K negative 1. When you actually do this reaction and measure data, you will actually just measure one rate constant, not three of them. So basically you will see the overall, the sum, or like, you know, the product of all of those k's together. So you'll just have one k observed, which will contain the k's of all those little steps. So just so you know, you'll only actually calculate one k if you do this reaction. All right, so let's do the last one. So this is the new one. So what's the rate law? Rate equals K, what number? 2 times M times A. Yes, because it's the second step is the slow step. Am I done? No, because M is not allowed. So we take the fast step. We set the forward overall rate to the reverse overall rate. So K1 times B equals what? K negative 1 times M. Because M is the product, right? But in the reverse direction, that product is now the reactant. What do we do next? solve for M. So M equals K1 over K negative 1 B. All right, plug that guy in, and we see that the overall rate is equal to K1, K2 over K negative 1, which again, you would just observe as just 1K when you do this experiment, times A times B. Okay, so let's compare these two rates that we just got. Okay, what's the overall order for this last one we just did? The overall order, 2. But the previous one, the overall order is 3. Yeah, so that's a big difference. Okay, so having a different proposed mechanism can have completely different results. You will see different experimental data depending on which mechanism is correct. Okay, so because you see, oh, in the last mechanism we did, A is a second order, but it is first order in this reaction. Or in this reaction over here, it's 0th order in terms of A. So if you change A concentration, you wouldn't see any change in reaction rate. So lots of ideas from previous concepts coming back. Okay. This is more likely how a exam question will be proposed. Here's my mechanism. There's the overall reaction. There's the experimental data. Does the data prove the mechanism is correct, proves it's incorrect, or is it consistent with the proposed mechanism? So there's lots of things to unpack here. We need to, 1, get the mechanism. We just did a bunch of those. So hopefully at this point you can just look at this and you know what the mechanism is. Or sorry, the overall reaction, the rate law, given the mechanism. Then we need to take the experimental data and figure out what the rate law is. So that was, remember I told you there's 3 types of methods we determine rate law. So that table is that first method, the method of initial rates, the initial rates. So we gotta do, it's basically 2 questions packed into 1, unfortunately. So let's do the easy one first. Let's determine, given the mechanism, what the overall rate law is. I hope you think it's easy, right? Because what makes it easy? The slow step is what? The first step. So the rate for this overall reaction should be K times concentration of NO2 times the concentration of F2. That's it. We don't even have to worry about the second step because it's fast. All right. Okay. Oh yeah, so the analogy I like to make with the slow step or whatever, if I had to make bikes, if that was like my reaction, I make bikes, right? Let's say the second step was just slapping a bow on a finished bike, okay? Okay, and so like my first step is building the bike. The second step is slapping a bow on it. What's gonna determine the overall rate of bikes produced? It's the first step, because the slapping the bow on it is not gonna change anything about that first step, okay? All right, so we figured out the rate law from the mechanism. Now we need to think back to that first method we determined rate laws. We need to use the experimental data. So remember how we did this? We locate a reaction where a reactant concentration stays the same. So we're able to isolate the order of the other reactant. So if I look at trials 1 and 2, NO2 stays the same, but how does F2 change? It triples. So then we inspect, okay, how does the rate change? It also triples. So what's the order of F2? 1, yay. Okay. Now how do I get the order of NO2? Yeah, let's look at trials 1 and 3 now. All right. So because in 1, what's special about trials 1 and 3? F2 stays the same. So now I can isolate the order of NO2. So I see, okay, F2 stays the same, so nothing there is changing the rate, the initial rate. I see that NO2 doubles. How does the initial rate change? It also doubles. So what's the order of NO2? 1, yes. So is this data consistent with the proposed mechanism? Yeah, so what's the answer? Is it A, B, or C? C, yeah. So note how I did not say it proves the mechanism's correct. We can't prove stuff's correct because we can't see atoms. That's it. So it's just a subtlety on language here. All right. Is it that bad? Is it that bad? Yeah. So this question, 2 questions wrapped up in one. Okay, great. All right, so let's pretend, we did the experimental data and we saw, oh no, it's 0th order in NO2. What would the answer be? It would be B in this, yeah, B, that it's incorrect, that they don't match. Remember, proposed mechanisms have to match experimental data. Okay, cool. All right, another one? Yes, another one. Another one. Okay. Here's the overall reaction. There's my mechanism. Here's the proposed rate law. Which experimental data is correct? Or wait, is the proposed mechanism consistent with this experimental data? So here's the proposed mechanism. Here's the data. Does it all match? First, so I gave you the proposed rate law. First, do you agree with this? Yes, because the slow step is the rate determining step. It's first order in NO2, first order in F2. So yeah, blah, blah. Okay, great. Here's the experimental data. Okay, so remember, this is the graphical method. Remember, straight lines on the graph typically means that is how it's graphed, tells you what the order for that reactant is. So here I'm telling you that if you graph the change in concentration of NO2, the natural log with time, you get a straight line. What does this imply? That NO2 is first order, yes. Okay, and I'm telling you F2 stays constant. Okay, well, what if I track the concentration of F2, 1 over F2 over time, and I see this change? What does that imply? That it's second order. So is this experimental data consistent with the proposed mechanism? No. What should the rate law be? It should be second order with respect to F2. It should look something like that. That's what it should be, because that's what the data says. So we need to go back, pick a different mechanism that fits that. But again, I told you, you're never going to actually make a mechanism. You're not ever going to do a mechanism. We would just have to find another mechanism that is consistent where the slow step gives us this overall rate law. All right, so that relates this last, determine the rate law from the mechanism to the graphical method of figuring out rate law. Right, so that's all 3. That's all 3. Okay, oh, another one. I love these. Okay, so it's the same reaction, slow reaction. Is this reaction coordinate consistent with this proposed mechanism? Yes or no? Yes. Why? Do you just say that? Do you just say that? So there's 2 things. This mechanism happens in 2 steps. Does this reaction coordinate? Yes, it happens in 2 steps. We got 1 step, 1 hill to go over, 2nd hill to go over. Yes. So it is in 2 steps. What's the other detail? Does it show the slow step in the, yeah, okay, yeah, all right, yeah. It shows the slow step in the correct place. That the slow step is the first step, and that's what the mechanism says. So, yes, okay. So if we increase the temperature of this reaction, which step is more sensitive to temperature changes? The first step, yes. So will this reaction be faster? Go fast? Yes, it will. Yeah, usually when you increase temperature, reactions go faster. Yeah, so in this case, step 1 is going to be more sensitive to temperature changes. So you will you see a big change in your rate constant or a small change in your rate constant? It should be big because our activation energy for that first step is fairly large. What if we change the temperature of a reaction where the second step was the slow step? Would you see as big of a change in K? Well, 1, would K go up if you heated up a reaction where the second step was slow? Yes, remember, because temperature always increases K. But you would not see as much a difference because it was, oh, I guess, no, never mind. You would see a difference. Yeah, you would still see a difference overall. Never mind. My brain was going somewhere else within there. Okay, what would the graph look like if it was The slow step was the second step. It would look something like, I don't know, like small hill, big hill? I don't know, something like that. Like that. That would be a slow step, second step. Okay, good, good. Okay, what method do we like the best for reaction rates? The first one, initial experimental data. Do we like the graphical method, or do we like this mechanism one? Mechanisms, really? I think a lot of folks, they think mechanisms is really hard. It's just really hard. You disagree. Okay, good. All right, so you can read that overview. Okay. All right, so, okay, we'll finish this chapter here. We'll talk about catalysts. So remember in that one reaction where we actually canceled out one of the reactants, and it was a product at the end. It ended up canceling out from the overall reaction. That was an example of a catalyst. So catalysts are substances you add to a chemical reaction to make the reaction go faster, right? But for a different reason. Because what are the ways we're able to make reactions go faster? What have we talked about this chapter? What can make reactions go faster? Temperature, yeah, heat it up, it goes faster. What else can change the rate constant of a reaction? Activation energy, all right? So this is the other idea, okay? So catalysts actually give a new reaction pathway for a reaction to take place. By doing that, we lower the activation energy. So the reaction goes faster. So I'll show you what that looks like on the next slide. But I just want you to know that we add a catalyst as a reactant, but then it's produced again as a product. So it cancels out of the overall reaction. Right? So we already talked about temperature changes affecting K. Catalysts affect activation energy. Right? That's how the reaction goes faster. Two types, homogeneous catalysts, all right? These are the most effective catalysts. If we're talking in terms of like money and like, you have an industrial process, you want to add a catalyst to make the reaction go faster so you can save money. Homogeneous catalysts are the best. Because they're integrated into the solution mixture itself. It's a homogeneous mixture. This is when they're all, the catalyst is in the same phase as all of the reactants. You get really good collisions happening when everything's the same phase. So for example, when your catalyst is a gas or in solution aqueous. Heterogeneous catalysts, I think they're more common when we think about catalysts, because when I think of a catalyst, I think of my car. Right, and the catalytic converter, which is like an object. It's actually just a hunk of platinum. Your catalytic converter is an example of a heterogeneous catalyst where it's typically a solid. So how your catalytic converter works is it takes gases that's produced from your exhaust, and the catalytic converter helps that reaction go forward to reduce the amount of noxious gases you produce. But the thing is that the catalyst is a solid and the reactants are a gas. So there's not good collisions happening. In this type of catalysis, all of the chemistry is done on the surface of your platinum catalyst. So the idea is, if you were to rip off your catalyst and look at it, it's not just a hunk of platinum. It's actually platinum in this honeycomb shape where it looks like a mesh screen. So there's a lot of surface area for that chemistry to occur. So that's how we can improve catalysis there. All right. So in general, catalysts work by lowering activation energy. That also increases K. It can also increase the number of effective collisions. So we can also increase that A term as well. And so how to identify a catalyst, it's usually a reactant and a product, and it's canceled out of the overall reaction. Okay, so types of catalysts. So I always think of my car because I hate living things, but enzymes in our bodies are also catalysts to make reactions in our body that aren't typically energetically favorable actually happen. And again, for the same reasons, enzymes work by both lowering activation energy and increasing A frequency factor. So here's an example of catalysis. This is hydrogen peroxide. Does anyone have some of that in their dorm room or at home? You've seen those bottles of hydrogen peroxide, okay? They're in those opaque bottles. Okay, So hydrogen peroxide, it's like kind of like a disinfectant, right? Like that's what we use it for. It looks like water, but it's not water. We pour hydrogen peroxide on our cuts and wounds, and you see the bubbles emerge, okay? So those bubbles are oxygen gas, all right? So peroxide is really not very stable molecule. So once you put it like on a cut or whatever, you produce water and oxygen. That's how you know the reaction is happening. That, you know, you put it on your cut, it bubbles, all right? That's how the reaction's happening. So this reaction, you produce a gas. But when you think about it, when you imagine what this bottle looks like in your medicine cabinet, is it producing oxygen when it's sitting in your shelf? No, it's not. We know it's not because the container isn't swelling up. It's not producing oxygen when it's just sitting on the shelf. So what that means is when it's in this bottle, you know, in the store, it's staying on this side of the reactant side of this chemical reaction. It's until we use it, it goes to the other side. So that's telling us that this activation energy is pretty large for hydrogen peroxide, and you're not going to go to products with it just sitting there. The difference is, well, okay, once you do use the peroxide and put it on your cut, then the reaction does go forward. You're essentially introducing a catalyst to the reaction to make it go forward. We're not actually like putting energy into the system when we use peroxide. We're giving it a different pathway to take to go to the product side. So let's see what that looks like. All right, so you see the red line, that's no catalyst. You see, okay, big activation energy, hard to get to the other side. The blue line is the reaction with the catalyst. You're giving it a new pathway, all right? So we see in that uncatalyzed reaction, we have one activation energy that relates to K. K is gonna be rather small, but with the catalyst present, we have this new activation energy, all right? It's smaller, all right? So it's going to have a larger K, all right? So a larger rate constant for that reaction to take place. You're giving it a new pathway. So yeah, that's why when you actually pour the peroxide on your blood or whatever, basically the blood is acting as the catalyst. But in this example, I'm giving you two different steps that the reaction is happening through this pathway. Given this diagram, what's the slow step? What's the slow step? The second step, yes. How do we know that? Did you just know? Yes, it's the bigger activation energy is the second step. Great. Okay, so that means, you know, we do this first step, we get these things, and we make our intermediates, and then we go to products with that second step. So based upon these reactions, these steps, what is our catalyst? It's not blood, but given these, the proposed mechanism here, what is the catalyst? Br minus, because it is a reactant and it's consumed. Or sorry, and it's produced at the end. Yeah, it's a reactant and it's consumed, but then it's produced by the end of the reaction. So you see it cancels out when you get the overall reaction. But then what is an intermediate? This is like my catalyst. Do we have an intermediate? Yeah, we have Br2 is our intermediate because it is produced in the first step, but then consumed in the second step. So the concentration of Br2 is going to be real high in that intermediate step right there. It's going to be real high right there, but we won't see Br2 as a reactant or a product here. Okay, good. Catalysis, good. So that's kind of combining all our ideas here in the Arrhenius equation. Reaction rates, everything. So you can see absolutely that the blue step, the blue reaction coordinate is overall faster. Okay, so that's the kind of, yes, this is the last thing. So how, I'll try my best to talk about enzymes in the body, but they work exactly the same as other catalysts. So in this previous example, oh, I should ask, the catalyst, is it a homogeneous or heterogeneous? Homogeneous, yeah, because everything's aqueous, everything's in water, so that's good. All right, so enzymes work exactly the same. We're giving the reactants a new pathway to get to products, but specifically how enzymes work is usually there's a pocket where your reactants fall into. So by those reactants going into the pocket there, we actually bring the substrates or the reactants closer together. If we bring the reactants closer together, what component of our Arrhenius equation increases? Is it the frequency factor of collisions, or is it activation energy? If we bring reactants closer together, A actually increases, so that's why the reaction speeds up. In the pocket, we also, in that reaction pocket, we can also orient the reactants in a way so we get effective chemical reactions occurring. So the orientation in the pocket actually also increases the A component. Right? And so the last idea here is when we have the reactants in the pocket, we can pre-weaken the chemical bonds within the pocket for the chemical reaction to occur. So what does that change in the Arrhenius equation? If we pre-weaken the bonds? Activation energy, yes. So it becomes easier to get over the hill. All right, so that's how enzymes speed up chemical reactions too. It's still the same process as we talked about previously. So I think there's just one slide left. It's the overview slide. So that means that chapter 14 homework is due on Monday. We will start chapter 15 next week, but the Tuesday before the exam, we will devote to chapter 13, 14 review for the midterm. All right?